One quick thing to note is that the determinant of any matrix is also the same as the determinant of its transpose. We remember a transpose is if you take the rows of a matrix and make them the columns. This is easiest to see in a two-dimensional example. The determinant of matrix ABCD is AD minus BC, which would be the same as the determinant of its transpose, which also comes out to AD minus BC. We can also show that this principle holds true for three-dimensional matrices, though it's a little more algebraically intensive. We can then generalize that the determinant of any square matrix is the determinant of its transpose. Now that we've learned how to compute the determinant, we can apply it to other areas of mathematics. You might be familiar with a concept known as the cross product from vectors. There is a major connection between the 3D determinant and the cross product. But some quick reminders from vectors. There are three standard unit vectors, meaning length 1, I, j, and k, where I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. These are three different notational systems for these unit vectors. Whether you just use the letter, you use angle brackets, or you use a vertical column as if it was a matrix. We can then imagine taking the determinant, where the top row is ijk, the second row abc, and the third row def. Using the method we learned in a previous video, we can find the determinant using cofactor expansion. If we find those 2D determinants, we can expand this expression to being in terms of I, bf minus ce, minus j, af minus cd, and plus k, ae minus bd. Just as a one step of clarification, you can factor out a negative from the j term to make them all positive. We actually recognize that this is the formula for the cross product of two vectors, being bf minus ce, cd minus af, and ae minus bd. Therefore, the determinant of a matrix where we write I, j, and k as row 1, and rows 2 and 3 are our two vectors, we can compute the cross product that way. The determinant is also helpful at finding different areas and volumes. Take, for example, a parallelogram in 3 dimensions whose sides are defined by the two vectors u and v. We recall that the area of the parallelogram is the magnitude of the vectors multiplied by the sine of the angle between. But we also remember that the sine of the angle between can be redefined as the magnitude of the cross product over the individual magnitudes of the vectors. Thus, the area of the parallelogram is just the magnitude of the cross product, and again, we can use the determinant now to calculate that cross product. In the special case that the parallelogram is actually in 2 dimensions, we can think a little bit differently about finding its area. We recall that the area of the parallelogram is equal to the magnitude of the cross product. However, if the vector only has 2 components for u and only 2 components for v, the cross product simplifies greatly when we use the determinant calculation. We see that it is equivalent to k times the smaller determinant of a 2 by 2 u1, u2, v1, v2. But remember, the cross product isn't what we're concerned with. We want the magnitude of the cross product. When we take the magnitude of this vector, which 2 of its components are 0, we just get that the magnitude of the cross product is the absolute value, or the positive version, of the third component, which is that smaller 2 by 2 determinant. And what we showed earlier is that the determinant of a matrix is the same as the determinant of its transpose. So we can put the vector u as the rows and find the determinant, or we could put the vectors as columns and find their determinant. So finding the area of any parallelogram is just a 2 by 2 determinant calculation in 2D, as long as you have the 2 vectors that define its sides. If the determinant is 0, the matrix is not invertible. We remember that we can use the matrix inverse in order to solve linear systems, as seen in the example here. If we want to isolate x, we need to multiply both sides of the inverse. This only works if the inverse exists, and an excellent way to check if an inverse exists is to find the determinant. So if the determinant is non-zero, a unique solution exists to the linear system. A inverse times B can only take one value, because if an inverse exists, it must be unique. If the determinant is zero, there may be infinitely many or no solutions depending on the type of problem at hand. You would then need to solve your linear system using row reduction, or Gauss-Jordan. Just to recap everything we've seen so far today, if the determinant is zero, the matrix is not invertible. It also can help us determine if there are infinitely many or no solutions, or if there's one solution to our linear system. We can use determinants to calculate the cross product. We can use the determinants for parallelograms and triangles, and use the cross product version of the determinant to find their area. In the case of a 2D parallelogram or triangle, we can use a 2D determinant, making the rows or columns the vectors that define the parallelogram/triangle. And lastly, determinants can be used to find the volume of parallelepipeds, aka 3D parallelograms, and tetrahedrons. The determinant of this 3x3 matrix, where the columns of the matrix define the three sides of the parallelepiped, the determinant of that matrix would give you its volume. For a tetrahedron, it's the same idea, except instead of taking the determinant, we multiply the determinant by a sixth. We hope you're enjoying our channel, The Kernel of Truth. If you haven't yet, subscribe below. Make sure to like this video and leave us a comment if there's some math you'd like to see.